Starting with confidence intervals, now we're getting into inferential statistics. What we want to see is if we collect some sample data, what does that tell us about the population? Now in our course, we're going to really focus on proportions and working with if we have some sample proportion, what does that tell us about the proportion for the population? So what we want to see is what does some sample proportion, which our notation is p hat. So what does p hat tell us about p? So again, we're trying to get to this form of statistics where we don't have to collect population data. If we take a good large sample size, random sample, if we have this good sample data, how can we use that to talk about the population? So what we're going to be looking at is confidence intervals, which means we take this sample proportion and we end up with creating this range around it for this kind of lower value and upper value that we expect for what's happening in the population. So when we do this though, whenever we run inferential statistics, we won't know anything for sure, meaning we won't be 100% confident in our answer. But with how we use statistics and how sampling works, we're going to have a very high chance of being correct with our solutions. But there is always going to be this chance that we're wrong as well. So based on what we talked about with our sampling distribution, the idea is if we have a good random large sample and we have this expected population proportion, whatever it is, because in this section what will happen is we won't know what that value actually is. But the idea is if we take a random sample from this population, we really expect to be close by. We expect to be somewhere in here when we grab this random sample. Yes, it is possible that we land way out here in the tail, but it's unlikely. It's an unlikely starting point for our sample that we took. So what we're going to have is a random sample. Let's say I took a random sample and I landed over here. This sample proportion that we get is our best estimate for what we know is happening in the population. Meaning, again, I want to think about this value for p that's in the population. I don't actually know what it is, but I took a random sample and I get out this sample proportion. So that sample proportion, we can call that the point estimate, is also called our sample statistic, some terminology you'll see there. But the idea is that collecting that random sample and getting this value for a sample proportion, this is our best estimate for our population value. But what we don't want to do is to say our sample proportion is equal to the population proportion. It could possibly be, but it's quite unlikely to have them to come out to the same exact number. So that's where we don't want to just say the sample proportion is the population proportion. What we want to do is think about this sample proportion that we're getting out, and we want to bring in some margin of error for it. So the idea being we want to go a little above it and a little below it and kind of create this window that would hopefully be capturing our population proportion. And I know I said hopefully it captures it, but based on mathematics, we'll have an exact idea of how likely it is that we're capturing that true population proportion. So this margin of error, and just as a reminder of notation here, so this symbol here is plus or minus, meaning we take our sample proportion and we'd add on some margin of error. So that's going to create some distance above it. So we get to this upper value that'll be a cutoff. And then the minus part is that we'd subtract that margin of error so that we go below that value as well. So we'd end up with this window that's making a lower bound and an upper bound, and then based on how that window is created, that true population proportion should be in there. And we're going to have this level of confidence with how sure we are. So what we're going to end up with in our calculations for confidence intervals is we're going to have an interval. So for our interval notation, we'd use parentheses, and then we're going to have some value that'll represent a lower bound, and then some value that would represent the upper bound based on our calculations. So our sample statistic, this point estimate of p hat, is our starting point. That's going to be in the middle. But then what we would do is add a little bit of error, subtract a little bit of error to create a range of values that our population proportion should be in between. So the idea is that when we get this interval of a lower bound to an upper bound out, our true population proportion should be in that interval. Now we'll have a confidence level attached to this. Like with this, we'll say blah, blah % confidence, which will be part of our calculation. So like a common one that we'll be using is 95% confidence, meaning we would be 95% confident that that true population proportion would be in that range there, which makes it a very strong statement. Then we'll play around with changing this number. We could be 99% confident or 80% confident. And we'll talk about what changing the confidence does to the interval. But we'll have this level of confidence for this range of values, but the idea is that we're taking this sample data and then allowing for some error to get this range of values. So part of this is that we need to understand how these samples would spread out. So this bell-shaped curve that I drew up above here is our sampling distribution based on our population proportion. And we're going to work with a similar idea here, except we have to keep in mind that we don't know what our population proportion is. Through this work, and next week as well with hypothesis testing, we want to imagine we don't want to collect our population data, we're just working with sample data. So this value for p hat, what we're going to work with is the idea that that should be very close to our population proportion. Now that case that I set out here, that little green dot that I drew, maybe we took a random sample and got that value out, even though it's incredibly unlikely. And if we create this range of values, what might happen is we don't actually capture that true population proportion. It's not landing in the interval there like it did for my first one that I drew. And this is a possibility. But this is where when we make our sentence, we're going to be careful so that we note what our confidence level is, because by saying we're 95% confident in this interval, simultaneously we're allowing for that 5% that we're not confident in the interval. So it would be this 5% chance that we're wrong. So with that, the confidence level will be important, and there's always going to be this chance that we're wrong with these extreme values here. So working with our sampling distribution of proportion, in terms of center of the distribution, well, we won't know our population proportion, but what we'll do is just work with the assumption. So we're going to assume that the sample proportion that we took out is close to our population proportion. So we're going to build things around the sample proportion that we're working with. So in terms of center of the distribution, we're going to use our sample proportion. Then for standard deviation, our terminology changes ever so slightly here, and that standard deviation is going to change to standard error. So if you remember with our sampling distribution of proportions, in the last videos, we used that population standard deviation for sample proportions, and it was the square root of p times q over n. What we're going to see in this section is very similar, but the idea is that we don't know what p is, which means we don't know what q is. So our notation for standard deviation, we call it standard error now, because we're basing it on sample statistics. And our formula for standard error looks like this, which is basically the exact same formula, it's just using the sample statistics instead. So standard error, and I might even switch between the two, standard error is a form of standard deviations. They're very closely related. It's just standard deviation for our sampling distribution used population values, and our standard error uses sample statistics, which is what we have to use here because we only have sample statistics. So that'll be the spread of our distribution and centered at our sample proportion. Now, to even draw that bell-shaped curve like I did in that previous picture there, I should have checked the central limit theorem. And that's going to be something that we need to do for each of our problems here, because we basically need to show that we do have a normal distribution of samples. So we'll have to check for independence, and we'll have to check for randomization. which again, for those two, just assume that they're there when I give you a problem in this section. You can just check those off. But the one that we'll need to prove is that we have a large enough sample size, so that's success-failure condition. And when we did this for sampling distribution of proportions, we took n times p, making sure that was more than or equal to 10, and n times q, and making sure that was more than or equal to 10. The only thing that's going to change here is, again, we don't know what those population values are, so just use the sample statistics instead. So checking conditions will be part of our work that we have to do before we can even find our confidence interval. So what I'm going to do here is go through an example to kind of show you the idea behind how this interval forms, and then we'll end up with a formula and the process will be a little more direct. But I wanted to give you some background of why we need to do it this way. All right, so we have a survey of 2,500 HR professionals and showed that 1,200 of them use social networking sites to research job applicants. So state the sample proportion. So sample proportion, which is p hat, we would take 1,200 out of 2,500, which will be 0.48. And then they didn't ask for this directly, but we're going to need it in our calculations eventually. If you take p hat, it's a good idea to just grab q hat, which again is 1 minus 0.48, so a 0.52. And then our standard error for sample proportions, we're going to take the square root of 0.48 times 0.52 over our sample size of 2,500, which will be a point, and this will round to 0.01, but just to show you some extra decimal places, because this ends up with a bunch of nines. If I wanted to round this to 4 decimal places, so cutting there, the 9 rounds that up to a 10, and then it carries and carries until you'd end up with a 1 there. So when you end up with a string of 9s, kind of end up rounding 1 less up to a 1, and the rest turn into zeros. All right, so that's kind of the setup of our problem. And now what we want to work with is the idea that we have the sample data, and we're getting at this idea of, from the sample, 48% of those HR professionals are using social networking sites to research job applicants. So what we want to get at is, what does this tell us about all HR professionals? We know this is true for 2,500 of them. What does it mean about the population? So what does this tell us about all HR professionals? All right, so what we need to do is look at our sampling distribution. See, how do we expect these proportions to spread out working with this sample data? And again, what we're going to go ahead and do is assume that the sample proportion we got is very close by to what's happening in the population. So first thing we should do before making our sampling distribution, for now it's for p hat instead of p like we did in the last section, first thing I need to do is check the conditions. Check that central limit theorem. So independence, and we could use that 10% condition. Sampling 2,500 HR professionals in the world is probably less than 10% of all HR professionals. Or you could say how they research job applicants would be independent of each other, but we'll be good there. Randomization, this should be a random sample, which it doesn't specifically say, but we'll assume that's good there. And then where we'll show some work is the success failure. So you would take the sample size of 2,500 times the 0.48, which would be that 1,200 that they got for the number of successes, and then 2,500 times 0.52 to get a 1,300, and both of those are more than or equal to 10. So that means now for my sampling distribution, I can draw a bell-shaped curve. So I know the samples would behave in this shape, which is exactly what we want. Now, for the center of the distribution, I'm going to use that sample proportion because that's our best estimate for what's happening in the population. And then for standard deviation, we're going to use that standard error that we found. It's that distance of 0.01. So we'll have a 0.49, 0.50, 0.47, 0.46. So with this, we get an idea of working with sample sizes of 2,500 and expecting this 0.48 to come through. How would samples of 2,500 behave? So what we're seeing here is a distribution of sample proportions using a sample size of 2,500 and assuming that our population proportion is about 0.48. All right, so there's our sampling distribution. Now what we're going to use here is the empirical rule that we talked about a few weeks ago. And we're going to use this just to get an estimate, and then we're going to improve it. So this will be the one and only time we use the empirical rule for making a confidence interval, and then we're going to make it more exact, because again, that empirical rule is just estimates. But the rules are kind of simple, so it's kind of a nice way to see the confidence interval without getting too far into the technical part of it, which we will get into eventually. So the question goes, where do you expect 95% of samples, basically, sampling distribution p-hats to fall? So 95%, that was our 2 standard deviation away rule. So within 2 standard deviations of the mean, we would have 95% of the data. So what I'm doing here is if I go 2 standard deviations, or in this case 2 standard errors below 0.48 and 2 standard errors above, that's going to capture about 95% of our sample values. So this is where we can start to see what I was talking about up above of having this kind of starting point and then going above and going below. So what we can start to see here is our point estimate and then this added margin of error to get this upper value and subtracted margin of error to get this lower value. So we could say is something about how, well, this is going to change into confidence. So let me go ahead and interpret this as like we are about 95% confident. I'm going to throw in that about there because we are using the empirical rule. So we are about 95% confident. And then what we'll have here is an estimate for what's happening for all HR professionals. The proportion of all HR professionals using social networking sites to research job applicants should be between this 0.46 and that 0.50, because we found that about 95% of samples land between there, which means our true population proportion should be between there with 95% confidence. So we're about 95% confident that, and I'm going to put this in terms of our population, the proportion of all HR professionals that use social networking sites to research job applicants, which I know is a long sentence. Let's see. Social networking sites to research job applicants is between and here's our interval where we have this lower bound of 46% and upper bound of 50%. So what we end up with here is a sentence that talks about our confidence level. How sure are we about what we're stating here? And then we're making a sentence about the proportion for our population. So this wording here about the proportion of all HR professionals is in terms of our population proportion. And then we have a range of values or an interval with the lower bound and upper bound. So let's just break down how these are really calculated, because we're going to move to is a formula. So this 0.46, or this 46% that we got out, what we really did to get that was we had our 0.48, and then to get 0.46 out, we had to subtract that margin of error. And that margin of error that we used to make this 95% happen, we needed 2 standard deviations, or in our case, 2 standard errors. So what I took there was 2 times 0.01. So that's really the calculation we did to get to that 0.46, so that 46%, is we took our point estimate, subtracted margin of error, which is made up of 2 of those standard errors. Similarly, for 50%, what we did is we had our point estimate, that 0.48, and then we added margin of error, which was 2 of those standard errors. So what I'm trying to get at here is, in terms of a formula, is we started with our 0.48, which was our sample proportion, and then we added and subtracted the same value that came from 2 times the standard error that we were using. So this is starting to get at our formula. In fact, if you peek down at the bottom of the page, we're getting very close to our formula right here. Just going to fill in some pieces. But in terms of our standard error, that's what's showing up right here in the square root. That's the formula for our standard error. P hat on the left-hand side, plus or minus, because we're going to be adding and subtracting this overall margin of error. What is going to change is here in the formula, you can see this Z star. Right now, we have 2 written there, and it's working with 2 right now because that's what the empirical rule told us. But again, that empirical rule uses estimates, so we want to make this better. Now you're seeing Z come through here in the formula, and it is because that is related to a Z-score. So remember, Z-scores are this distance away from the mean in terms of standard deviations. So this 2 right here is this Z-score that's saying go 2 standard deviations above, 2 standard deviations below. So it's kind of giving you this distance of how many standard errors to go. So that is a Z-score. However, based on the empirical rule, it's a little bit inaccurate. So what we want to do is improve that value. So let's improve on that value of 2 there for our calculation. But everything else around it's going to stay the same. So just to show you where we're headed. So we want to have P hat plus or minus. And then this is our unknown here of how are we going to improve that number of 2. And then we're going to multiply that by our standard error. Okay, so for our sample proportion, what we want to do is go to our standard normal curve. So we want our bell-shaped curve with a mean of 0, standard deviation of 1. And what we want to do is, if 0 is in the middle here, we want to go away from that value, and we want to move away from it so that we have 95% of our data centered right there. And that cutoff that centers that 95%, that is going to be our critical Z-score. So we want a Z-score there that traps 95% in the middle. Now on the left-hand side, it's also over there. It's just the negative and positive version of that number because we're symmetric across 0 there. So what we want to do is find that critical Z-score, and once we find that, that will replace this number of 2. So we're expecting a value close to 2 here is the idea. And now this is where we go to Staplet. So we go to Staplet, probability, normal distributions. This is the case where we know the area under the curve. So we want to calculate a value corresponding to an area. We have a mean of 0, standard deviation of 1. And what we're looking for is we want a central area. So we're going to switch to a central area and change this to 0.95 for that 95% confidence that we're looking for. And there we can see our range from negative 1.96 to positive 1.96, which makes sense because that's very close to 2, but this is more accurate. So our critical Z-score here is a 1.96. So let's see how this calculation comes together. So we're plugging in our critical z-score right here. So plugging in our numbers, p hat, our sample proportion was a 0.48. Then we go plus or minus, our critical z-score is 1.96. And then we'll have our standard error, which is the big square root, with p hat times q hat all over our sample size of 2,500. So simplifying this down, my recommendation is plugging everything on this right-hand side into the calculator and getting a number simplified there. So we are going to kind of simplify in the middle of our work, but if we keep enough decimal places, it'll stay accurate. But where this is nice to simplify, this is called our margin of error. And sometimes we want to know that value for our calculations, or even later on, we'll adjust that value and see what changes to our numbers there. So what I do for my next step is I keep 0.48, the plus or minus, and then I plug that into a calculator. And this is where I like to use the Desmo Scientific calculator. So just to see that value, we'd have a square root, and then, we need the 1.96 out front, and then 0.48 times 0.52 over 2,500. So we have a margin of error of 0.019, and we'll round that to a 6 at the end there. So if I wanted to know my margin of error, this has a 1.96% margin of error. And then what we want to do is add and subtract that value. So we're going to separate into two calculations here. On the left-hand side, we'll have the subtraction. We always want to list the lowest number first, and then add on for the larger number on the left-hand side. So if you have everything typed into the Desmos calculator, this is where it's nice because you could just go 0.48 minus, so you see a 0.4604, and then you can just edit that to a plus, and we'll show you the other value. But it's nice to have this step of seeing that margin of error in between rather than just one big calculation. So our lower bound is going to be a 0.4604 and upper bound of 4,996. So when we go on to make a sentence here, we would say from 46.04% to 49.96% for our final calculation. And that is our more accurate confidence interval, so that we're using exactly 95% of values using that 1 point. So just to summarize, the formula that we're getting at for our confidence intervals, it's going to come from this breakdown of taking your sample proportion, or that point estimate, plus or minus some margin of error. That margin of error comes from this right-hand side here, where you're going to take some critical z-score. Now that critical z-score is going to come from your confidence level, in that what we'll practice is whatever your confidence level is, that's going to go in the middle. And then your critical z-score is the cutoff on this right-hand side here. What we'll see is on that left-hand side, it comes through as well. It's just the negative version of that number. But we want to center that confidence level, and the z-score will be the cutoff there. So the critical z-score times the standard error, that'll all together give the margin of error. Be careful of terminology there, because margin of error and standard error sound very similar, but they're different. Basically, margin of error includes the critical z-score. Standard error does not include the critical z-score. So this will be the formula that we use: sample proportion plus or minus z star times the square root. With these problems, will be given at the beginning of the problem. We'll have information for sample size, p hat, which if we have p hat, then we have q hat. So really we'll have about everything. The one piece we'll need to fill in the blank is when they tell us our percent confidence. That'll lead us to a critical z-score. So then it's just a matter of checking the conditions, making sure we pass that central limit theorem, plug in values into the correct spot, and then making a sentence answer. So that's a little background on confidence intervals, and then we'll continue on the next video.